Hello students, welcome to another session of online class. Today we'll start our second module. So the second module deals with the electric flux, flux density, Gauss's law and divergence. So in today's class we'll discuss about electric flux and flux density. Starting with we have some experiment done by Faraday. So this image what is shown here is Faraday's apparatus, nested sphere apparatus to study electromagnetic induction, and in this one he had two. Oh, this is the entire setup. This one is the entire setup. So in this, it is like two hemispheres. One is this one, another one is this one. Inside we have a small sphere like this, and in between the sphere you have a separation material which is made up of non-conducting material. So this one and this small sphere are metallic, and the inner sphere, the separation between the inner sphere and the outer sphere is a non-conducting material. So what he did is he charged the inner sphere, that is the small sphere, to a positive charge q, non-charge. He knows what is the value of that charge. Okay. Now uh, once he charged this one, he kept this one with the dielectric material, so that this inner sphere and the outer sphere doesn't come to contact with each other, and he covered this one with the outer hemisphere like this. So this is charged. After that, to the bottom sphere this is kept, on that the charged sphere is kept. So proper care is taken to isolate the charger, so that the charge will not get uh, shorted or get discharged through the body. So using proper isolating materials, it is kept here, and this lid is covered. So now for an instant of microseconds, he took a wire and just touched with the ground, so that whatever charge is here will be discharged to the ground. And then he removed the inner sphere from the interior body and measured this charge of this particle. So this is the experiment what he has done. So the steps are like: charge the inner sphere, keep it isolated from the outer sphere, close the outer sphere, momentarily discharge the, so for an instant just touch with the ground, okay, and remove the hemisphere and remove the inner sphere, and he measured what is there in the outer sphere, okay. So what was the outcome of this experiment was he got some charge, same charge q in the outer sphere. We know that the outer sphere was not connected to the inner sphere by any means. There was an insulating material between the inner sphere and outer sphere, but there was electric field due to the inner sphere, and due that field induced some charge in the outer sphere. So there is something which flows from the inner sphere to the outer sphere. So that thing, or that quantity which flows from inner sphere to the outer sphere, was represented as flux, electric flux, or displacement, electric displacement or electric flux, represented as psi. Okay, Greek letter psi. So psi is the electric flux. And what is the magnitude of psi? How much electric flux passed from the inner sphere to outer sphere? How much charge passed from the inner sphere to the outer sphere? So if you have a sphere like this inner sphere, there is isolating material in between this, and this is charged q plus q, and he observed that the minus q charge is developed at the outer sphere. So his observation is that the outcome is that something flows from the inner sphere to the outer sphere through the dielectric material. That flow is called electric flux. And how much it flew from the inner sphere from the to the outer sphere, what quantity it flow from inner sphere to the outer sphere is nothing but the same amount. the charge amount. So he represented psi will be Q. Okay, since Q is coulomb, the psi is electric flux also has a unit coulomb. Okay, so psi is nothing but the flow of flux electric field from one charge to another one. So that flux is nothing but Q, and it has a unit coulomb. So if you have 5 coulomb charge here, the outer sphere will get 5 coulomb. If you have 6 coulomb charge here, the outer sphere will get 6 coulomb. So something which flows from 5 from the inner to outer will be the same amount as the charge. So that is why he represented it as psi is equal to Q. Okay, now we will define flux density. Now we have inner sphere of radius A and another sphere, outer sphere of radius B, assume. Now the charge produces fluxes, so that is what we have learned now. So that flux is uniformly distributed throughout the surface area like this. So what is the surface area of the sphere? For a radius r, the sphere surface area is 4 pi r square, right? So in this case, the flux is uniformly, flux is nothing but charge. Charge is uniformly distributed over this area. So there will be some uniform distribution. What is the this is distributed over the area 4 pi a square. Now you can find a quantity called Q divided by 4 pi a square. That will be the density of flux in the surface. So if you can see here, it is more denser in the inner sphere, and as you approach the outer sphere, the density reduces, right? So that is a vector quantity. So this is per area, right? So area is a vector quantity. So this quantity Q by 4 pi r a square is called flux density. Why it is represented as d? Because it is flux was initially called displacement flux, so that is why this vector is called the displacement flux density. So this is a vector and it is given by d by 4 pi a square ar cap, where ar cap is the direction of outward the radius of the sphere. Okay, so this quantity is called Q by 4 pi a square for this inner sphere. For outer sphere, if the radius is b, what is d there at the outer sphere? This is inner sphere. Outer sphere, d is equal to Q divided by 4 pi b square ar cap. So we found that for a charge Q with radius a, the flux density is Q by 4 pi r square a square ar cap. For radius b, which also consists a charge q inside, so the flux passing through will be the q only, so it will be again q by 4 pi b square. Now assume that you can consider an imaginary sphere of arbitrary radius r at anywhere between b and a. So anywhere between b, or it is anywhere outside a. If you consider here also any arbitrary radius r, the flux density will be, as we discussed here, the flux density will be d is equal to q by 4 pi r square ar cap. So this is the expression for flux density due to charge q. Okay, now we will find what is the relationship between electric field intensity and d. So we have discussed that if there is a q charge at a distance r, the electric field, the flux density d is given by q by 4 pi r square ar cap. And from the q at a distance r, if the electric field intensity E is given by this we have discussed q by 4 pi epsilon 0 r square a r cap, right? So if you see these equation, they are similar. The only thing is there is an epsilon 0 extra. So if you find d by e, first equation divided by second equation, q gets cancelled, 4 pi gets cancelled, r square gets cancelled, and air cap. So since they are in the same direction, we can cancel them each other. So only left is 1 divided by epsilon 1 divided by 1 by epsilon 0, or it is epsilon 0. So d is equal to epsilon 0 times e, right? So this is a very important relationship. So what you have to do, write the expression of d, write the expression of e, and divide those equations. You will get the relationship between d and e. Since e is equal to q by 4 pi epsilon 0 r square a r cap for any condition, and we studied that dq by dv equal to rho v. From this you will get dq is equal to rho v dv, and if you substitute that here, you may get or q equal to integral rho v dv over the volume. So E is equal to integral over the volume q by 4 pi epsilon 0 r square a r cap rho v dv, right? Same way we can describe d is equal to integral over the volume rho v dv divided by 4 pi epsilon 0 4 pi r square, because d is equal to epsilon 0 times e, so epsilon cancels a r cap. So you can calculate with this one. So that is the we will be more dealing with the d rather than the e, because d has no epsilon 0, so it is not having a epsilon 0 time. But this is limited only for the free space or vacuum cases. If the direct medium is there, this equation will slightly differ, that we will see later. But for the time being, it will be, we will be discussing only regarding the free space. We will work out some problems regarding to flux density. So calculate d in rectangular coordinate at point p2 minus 36 produced by a point charge qa is equal to 55 millicoulomb at a q 2 minus 2 3 minus 6. So we know that d is equal to epsilon times e. Since e is so what kind of charge is this one, either point charge or line charge or volume sheet charge? Here it is clearly mentioned it is a point charge, so we have to use the expression for e as q by 4 pi epsilon 0 r square a r cap, right? So we will use the same, but we this is mentioned in terms of a rectangular coordinate system, so we need to put what is r here. So r is actually x ax cap plus y ay cap plus z az cap, and that is in the case if the charge is at origin. But we have the charge is given at a point P, right? So this is x1 y1 z1, so our r will be x minus x1 ax cap plus y minus y1 ay cap plus z minus z1 az cap, right? So ar cap is vector r divided by mod r. So we have to calculate mod r also. So mod r is nothing but square root of x minus x1 square plus y minus y1 square plus z minus z1 square, right? So substituting this in the expression of e, So it will be epsilon 0 q by 4 pi epsilon 0 uh, mod r square into vector r divided by mod r. So it will be epsilon will cancel, so q r divided by 4 pi mod r cube. So this is the expression which we will be using for a point charge, right? I think this is clear for you. In the problem, we have to find the electric field intensity at a point P, that is 2 minus 3 6 due to a charge of Q equal to 55 millicoulomb at kept at a point Q minus 2 minus plus 3 comma minus 6. So these are the values given. So this is actually where you have to calculate. So it is called X, Y and Z. So this is 55 millicoulomb is the charge, and here it is the point at which the charge is kept. So that is x1, y1, z1. So the vector r is x minus x1, that is 2 minus 2 will be 4ax cap plus y minus y1, so minus 3 minus, so minus 6ay cap, and z is 6 minus minus 6 plus 12az cap, and mod r is equal to square root of x 4 square plus 6 square plus 12 square. So that will be square root of 16 plus 36 plus 144. So which will be 196. So square root of 196 is 40. So we have the expression d is equal to q by 4 pi r cube into r vector r. So that will be q is 5 milli 55 milli 55 into 10 raised to minus 3 divided by 4 into pi into 14 cube into 4ax cap minus 6ay cap plus 12az cap. So if you simplify this one, you will get a value like 6.38 ax cap minus 9.57 ay cap plus 19.14 az cap. So this is the expression, final expression for D. Okay. So the next question is calculate vector D flux density in rectangular coordinate at a point P 2 minus 36 produced by a uniform line charge rho LB is equal to 20 millicoulomb per on the x-axis. So we know that the expression for E is general expression is 2L by 2 pi epsilon 0 rho a cap, and when the line passes through x-axis or parallel to x-axis, we have discussed this one, that expression will be rho L by 2 pi epsilon 0. Since this is along the x-axis, there won't be x component, so it will be y ay cap plus z az cap divided by y square plus z square. Since this is along the line, there is no x1 y1 z1 term. So this is E, so D will be epsilon times E, so it will be rho L by 2 pi y ay cap plus z az cap divided by uh, y square plus z square. So what is the value of rho L? Rho L is 20 into 10 raised to minus 3 divided by 2 pi into y is much. We have to calculate at a point 2 3 minus 3 6. So this is x, this is y, this is z. So y is minus 3 ay cap plus 6 az cap divided by y square plus z square, that is minus 3 square is 9 plus z square is 36. So 20 into minus 10 raised to minus 3 divided by 45 90 pi into minus 3 ay cap plus 6 az cap, which will give you a value, final value. If you simplify this one, you will get minus 212 ay cap plus 40 424 az cap micro coulomb per meter square. So that will be in micro. 10 raised to minus 3 will be 10 raised to minus 6 it will become. So if you simplify that, it will become like this. So that is the vector d. So unit of d is, psi by area. So psi is coulomb and area is meter square. So coulomb per meter square is the unit for d. So remember this. This is the method is just simple. You know the expression for E. So T is equal to epsilon 0 times E. So you can simplify and get the value. So that is the how you have to calculate D. That's all for today's class. Thank you.